Lesson: AI techniques for vulnerability identification. Artificial intelligence has emerged as a pivotal force in the domain of cybersecurity, particularly in identifying vulnerabilities within complex systems. Vulnerability identification is a critical aspect of cybersecurity, as it involves pinpointing weaknesses or flaws in a system that could potentially be exploited by malicious actors. Traditional methods of vulnerability identification, such as manual code reviews and penetration testing, while effective, are often time-consuming and require substantial expertise. AI, with its ability to process vast amounts of data and learn from patterns, offers a transformative approach to enhancing vulnerability identification processes. AI techniques for vulnerability identification leverage a range of methodologies, including machine learning, deep learning, and natural language processing. These techniques can analyze large datasets, recognize patterns, and predict potential vulnerabilities with a degree of accuracy and efficiency that surpasses traditional methods. Machine learning, for instance, can be employed to analyze historical data on known vulnerabilities and exploits, enabling the development of predictive models that can identify similar patterns in new software or systems. Supervised learning, a subset of ML, is particularly useful in this context, as it involves training a model on a labeled dataset where the outcomes are known. This trained model can then be used to predict vulnerabilities in unknown datasets. Deep learning, a more advanced subset of ML, utilizes neural networks with multiple layers to analyze complex data. In vulnerability identification, deep learning can be applied to tasks such as static code analysis, where the system reviews the source code for potential vulnerabilities without executing it. This technique can identify subtle patterns and anomalies that might be missed by human reviewers or simpler automated tools. For example, a deep learning model trained on a large repository of code containing known vulnerabilities can learn to detect similar patterns in new code, thus identifying potential security flaws. Natural language processing, another AI technique, can be used to analyze textual data such as software documentation, bug reports, and security advisories. NLP can extract relevant information, classify it, and provide insights into potential vulnerabilities. For instance, an NLP-based system could scan through vast amounts of textual data to identify mentions of new vulnerabilities, their characteristics, and potential impact. This information can then be used to prioritize vulnerability management efforts, ensuring that the most critical vulnerabilities are addressed first. AI techniques can also enhance the process of dynamic analysis, where a system is tested in a runtime environment to identify vulnerabilities that may not be apparent through static analysis. For example, AI-driven fuzz testing involves providing a system with a wide range of unexpected or malformed inputs to identify how it responds. By learning from past tests and continuously adapting its approach, an AI-based fuzz tester can uncover vulnerabilities that might be missed by traditional fuzzing methods. This dynamic and adaptive approach makes AI-driven fuzz testing particularly effective in identifying complex, multi-step vulnerabilities that require specific sequences of inputs to exploit. The effectiveness of AI in vulnerability identification is substantiated by various studies and real-world applications. For instance, a study by Lee et al. Demonstrated that machine learning models could achieve high accuracy in predicting software vulnerabilities by analyzing code metrics and historical vulnerability data. Similarly, a research project by Zhou et al. Highlighted the potential of deep learning models in detecting security vulnerabilities in Android applications, achieving a detection accuracy of over 90%. These findings underscore the potential of AI to significantly enhance the efficiency and accuracy of vulnerability identification processes. Moreover, AI techniques can be integrated into continuous integration, continuous deployment pipelines to provide real-time vulnerability identification and mitigation. This integration ensures that security is embedded throughout the software development lifecycle, rather than being an afterthought. For example, an AI-based static code analysis tool can be integrated into the CI/CD pipeline to automatically review code changes for potential vulnerabilities before they are deployed. If a vulnerability is detected, the system can alert developers and provide recommendations for remediation, thereby reducing the risk of security flaws being introduced into the production environment. Despite the significant advantages of AI in vulnerability identification, there are also challenges and limitations to consider. One of the primary challenges is the quality and availability of training data. AI models require large data sets of labeled vulnerabilities to learn effectively, and obtaining such data can be difficult. Additionally, AI models are only as good as the data they are trained on. If the training data is biased or incomplete, the model's predictions may be unreliable. Another challenge is the interpretability of AI models, particularly deep learning models, which are often considered black boxes due to their complex and opaque decision-making processes. This lack of transparency can make it difficult for security professionals to understand and trust the model's predictions, potentially hindering its adoption. Furthermore, while AI can significantly enhance vulnerability identification, it is not a panacea. AI models are susceptible to adversarial attacks, where malicious actors manipulate inputs to deceive the model and evade detection. For instance, an attacker could introduce subtle changes to the code that are designed to bypass an AI-based static analysis tool. To mitigate this risk, it is essential to continuously monitor and update AI models, incorporating new data and techniques to improve their robustness and resilience against adversarial attacks. In conclusion, AI techniques offer a powerful and transformative approach to vulnerability identification, providing the ability to analyze large datasets, recognize patterns, and predict potential vulnerabilities with unprecedented accuracy and efficiency. Machine learning, deep learning, and natural language processing are particularly effective in enhancing static and dynamic analysis processes, enabling real-time vulnerability identification and mitigation. However, the successful implementation of AI in vulnerability identification requires careful consideration of challenges such as data quality, model interpretability, and adversarial attacks. By addressing these challenges and continuously refining AI models, organizations can leverage AI to significantly enhance their cybersecurity posture and proactively address emerging threats.